Hey everybody, welcome back to another fun and exciting geometry class. Today we are going to kind of transition out of constructions a little bit, and we're going to actually talk about what's called axioms. We're going to talk about what's called postulates and what are called informal statements. And I know those words sound big and they're new and maybe you haven't even heard any of them before, but I promise you that it's not as bad as it sounds, okay? And so we are on page number 38 in your books if you want to follow along. And I really recommend that you follow along. I wish that I could put this up on the screen, but just due to copyright laws and things, I can't. So if you'll follow along in your book, I will try to keep you engaged with where we are, let you know what part we're on. But it is very important that you have your book open. If you're watching and you don't have a book for some reason, I really highly suggest that you get one of these books. If you're in my class, you should already have one. But if you're just watching the YouTube video, get one of these books. It's an Abeka book. And so you can order it from their website, Plain Geometry. Very, very good book, and it'll teach you a lot of things, and it's good to have it as you're going through this. All right, well, page 38 is where we're at. When in geometry, in math in general, certain things are stated, certain things are said, and you just don't have to prove that. You don't have to, like, explain why, okay? Like, for example, I'll give you just a really, really basic one. 6 times 6 is 36. I don't have to explain it. I don't have to show you why. I don't have to cut out little squares and paste them all together and show you that if I take these and I multiply them and I add them 6 times that I get 36. I don't have to do any of that. Why not? Because that's a universal truth that everybody knows. Every calculator in the world knows it. Every computer in the world knows it. And every student that's passed about 3rd grade knows it. Okay? And so we memorize that. It's a fact. It doesn't have to be proven. And that would be called, it's a type of an axiom, something that's never, look down at the screen here. I wrote the word axiom. These are general statements, typically mathematical in nature, that don't need to be proved. There's no need to prove these, okay? And so let's go through some axioms that we need to know. We don't need to prove these, but we need to know these. And most of the time, most of these, when I go over them, you're going to be like, yeah, of course, because they are basic and they are things that, but in order to go to the next step, and the next step, if you look through your book in chapter number 2, it starts out in what's called proofs. We have to start proving things. So before we can get to that, we have to talk about the things that we don't have to prove. Okay, the axioms, postulates, and statements that we will be talking about today. All right, so axiom number one, quantities that are equal to the same quantities or to equal quantities are equal to each other. So quantities that are equal to the same quantity. And an easy way for me to kind of explain this one is something like this. Quantities would be like 5 plus 3 that are equal to the same quantities. Now, we might write these a little different, but we might say 3 plus 5. Those are the same quantities. And we wrote them in a different order, but they're the same. And so we know that those things are going to come out equal to each other, okay? And so this is a mathematical thing that we already know. Number 2. If equals are added to equals, the sums are equals. If you're thinking, I've heard that before, you're right. If you go back to page number 8, that was principle number 7. And so principle number 7, we talked about principles earlier, principles of equalities. Some of these are going to have overlapping characteristics. And again, I'm not going to spend much time on these. Axiom number 3. If equals are subtracted from equals, the remainders are equal. That's the subtraction axiom. The other one was the addition axiom. The multiplication axiom number 4, if we double something, or really multiply it by anything, triple it, quadruple it, if we multiply it, everything by 10, as long as we're multiplying everything by the same thing, then it stays equal. Number 5 is the division axiom. Halves are equal to halves, or if you take 1/3 or 1/4, whatever you take, it stays equal as long as you do it to everything. Number 6, the whole is equal to the sum of its parts. The whole are equal to the sum of its parts. Number 7, the whole is greater than any of its parts. So the whole line is always bigger than part of the line. It has to be. Number 8, a quantity may be substituted for its equal in any process. That's the substitution. This is a really, really important one right here. This one you're going to use all the time in geometry, so make sure that you pay attention there, highlight that in your book. Number 8, the substitution. We substitute things in, like let's say that we have 2 plus 3. At any point in time, we can substitute in what? Well, we could substitute in 5 because 2 plus 3 equals 5. So at any point in time, we can substitute in anything that equals that. We could also substitute in 1 plus 4 because it also equals 5. So we can change those values as long as we're not changing what it equals, the end result. Number 9, axiom number 9, if the first of 3 quantities is greater than the second quantity, and the second is greater than the third, then the first is greater than the third. And that was again back there in those principles as well. I think that was the last principle. I don't remember which one it was. Number 11. Yes, principle number 11. So same thing there. You can go back and watch that video for an explanation, or just go back and look in your book. All right, so those are the axioms. Those are basic axioms of mathematics. Nobody challenges those things. They're true all the time. The next thing that I want to talk about are postulates. Postulates. Now, these are not mathematical in nature. These are geometric in nature. So these are geometric assumptions that do not need to be proved. In other words, these are things that I can just say and everybody believes me. Okay? And they believe because it's true, because somebody else proved them, or because they're so basic that nobody needs to prove them because everybody understands this. Number 1, through 2 given points, one and only one line can be drawn. All right, so if we have 2 points, you can only draw one straight line through those 2 points. We've already talked about that as well. Postulate number 2. A straight line is the shortest line that can be drawn between 2 points. And again, we've talked about that one as well. If you have 2 points, I can draw other lines. Now, they might be curved, or they might be, crooked, or they might be, in a circle, whatever. So I can draw lines, but only one straight line, and that is the shortest point. The shortest way to get to those 2 points is that straight line. Number 3, a straight line may be extended indefinitely, or it may be limited by a point. And we've talked about that. So we have the line segment, and that's limited by points. The straight line goes in both directions infinitely, but it can be limited. It can be limited by what we call a point. Postulate number 4, a circle or part of a circle may be drawn about any point or around any point at the center and with any given radius. So if I take a point, I can draw a circle around that point with any given radius. It doesn't matter if it's a small circle, doesn't matter if it's a huge circle. I mean, the earth is a circle, okay? And it's a sphere actually, but it's a circle, okay? The Bible talks about the Lord sits on the circle of the earth. People that studied the Bible knew that the earth was a circle before a lot of people. Science was way behind. Christopher Columbus read the Bible and he said, I know the world's a circle. So the world's a circle or a sphere. And so at the center point, it's around it at a certain radius. Now, the mountains and the oceans and things kind of change the top of the Earth, but the idea is that it's a circle and the center point is the radius. So you can have a huge circle, a massive circle the size of the Earth, or you can have a tiny little circle all around one point. Postulate number 5. This is the most important postulate that you have. You will use this postulate all through the book, I promise you. And all you have to do is write, when you're writing your proofs, all you have to do is say postulate 5. And I'm going to be like, okay, yeah, we all know postulate 5 because we use it so much. Here's postulate number 5. A geometric figure may be freely moved in space without changing its size or its shape. So I can take a triangle and I can move it wherever I want to move it. And I can do that without changing its size or shape. Basically, it stays a stationary figure and it moves through space. So I can take it and remember the corresponding parts. I can, in my mind or in reality, I could actually take it, move it in space, and drop it down on another triangle, and the corresponding parts match up. So postulate 5, very, very important for you to understand. All right, just a few informal statements. What's an informal statement? Information that are natural, or information that is natural conclusions based on axioms and postulates. So we had the axioms and postulates. We just kind of went over those. Informal statements are basically statements based on those axioms and postulates. If you look here on page number 39, you're going to see, oh, informal statement number 2. Where's informal statement number 1? Well, we've already had it. Maybe you missed it, but we talked about it. And that says that all triangles, all the angles of a triangle equal 180 degrees or equal a straight angle. That was informal statement number 1. So here on page 39, informal statement number 2. 2 straight lines can intersect at only one point. So if you have 2 lines and they're straight, they are going to intersect at only one point. Now, they don't have to intersect. You can have what's called parallel lines that never intersect. They just go in the same direction. But most lines are going to intersect at some point in time. Remember, because lines go indefinitely. So unless they're perfectly parallel, if they're just a little bit off parallel, they will intersect at some point. Maybe a long time, maybe into outer space that they would finally intersect, but they will intersect unless they are perfectly parallel. And they will only intersect one time. They can only intersect one time as long as they're straight. Informal statement number 3 says a line can be divided into 2 equal parts, but only at only one point, excuse me. So like you can't, like, let me show you this. You can't like divide a line. So here's a line, and I can't divide that line right here and say, oh, that's 2 equal points. No, no, no. It would have to be at only one spot. Because if I go to the right or to the left, now they're not equal anymore. I can only divide a line in half at one point. Statement number 4, a given angle can be divided into 2 equal parts by only one line. Same thing there, kind of with the line, but an angle this time. Informal statement number 5, all straight angles are equal. That makes sense because they're all equal 180. So that would have to be the same. Informal statement number 7, only one perpendicular can be drawn to any one point through any one line at one given point. So here's that. In other words, if I have a point on this line, I can only draw one perpendicular line through that point. Okay? Because if, there we go. There's a perpendicular line. Well, it was until I messed it up. There we go. All right. I can't, any other line I draw through there is not going to be perpendicular. I can only draw one perpendicular through that point. So that's an interesting one. something that maybe you've never thought of before. But it's true. Informal statement number 8, complements of each angle or of the same angle are equal. So if I have an angle and my angle is, let's call this angle 40 degrees. Well, the complement of 40 degrees is 50 degrees because complements equal 90. And so every complement of that angle, no matter what, no matter if, it's this direction, no matter if it's this direction, it doesn't matter. They're all going, every complement of 40 is going to equal 50. It has to. No matter what it looks like, no matter what direction it's facing, it has to equal 50 degrees. Let's see, informal statement number 9. Supplements of equal angles or the same angle are equal. So same thing there, only with now supplements instead of complements. Informal statement number 10, the sum of all the angles about a point on one side of a straight line through the point is a straight angle. So like if you have the sum of all the angles about one point on one side of a line, so in other words, if you have multiple angles on the line, if you add them all up, whatever this is, 40, 50, 30, 60. It's always going to equal 180. It has to equal 180 because that's a straight line over here. It's a straight angle. Informal statement number 11. The sum of all the angles about a point is equal to 360. So again, we just talked about that a second ago, but if I have a point and I add up all of those angles, it's always going to equal 360. Why? Because the circle equals 360. Informal statement number 12, if the sum of two adjacent angles equals a straight angle, their exterior sides form one straight line. If the sum of two adjacent angles equals a straight angle. So there's two adjacent angles that equal a straight angle. Their exterior is going to form a straight line. And so the interior is going to equal the exterior. Why? Because the interior is 180 and the exterior is also 180. Let's see, informal statement number 13. We're almost done, just two more, hang in there. When two straight lines intersect, the vertical angles formed are equal. So if two lines intersect each other, these angles right here are called vertical. Vertical angles are always equal to each other. They have to be. Okay, so that's informal statement number 13. That's an important one too. We use that a lot. Vertical angles are equal. And then informal statement number 14, the sum of two sides of a triangle is greater than the third side. And that one's interesting too. But if I have a triangle and I say, okay, so this side is 10 and this side is 11, those two, when I add those up, that it has to be greater. So these two together are going to equal 21. This side cannot be, so this side has to be less than 21. Has to be less than 21. And we'll talk about why all that works like that, and that's something that we'll come up to a little bit later. But the sum of two sides of the triangle is always greater than the third side. So this third side would have to be, x would have to be less than 21. It can't be more than 21. Okay, and that goes, it's due to the angles and it's due to some other things, because if it's not, then you'd end up with a different shape, or you'd have an obtuse angle, or two obtuse angles or something like that. So we'll get to that, but just for now, just accept that as as reliable and as accurate. Okay. All right, there was lots of stuff there. I hope you learned it all. If not, go back and freshen up on that, read that over, and you can even watch parts of the video again if you didn't understand certain things. Okay. All right, we'll see you later. Have a good one. Bye-bye.